Imagine two flashes in an otherwise empty universe. One appears, then the other. Did the first cause the second? At first, the answer seems to depend on sequence alone. If one happened earlier, perhaps it could have produced what came later. But modern physics demands more information. We must know how far apart the flashes occurred, how much time separated them, and whether any signal traveling at or below the speed of light could pass from one event to the other. That requirement changes the question. An event may occur earlier according to one observer, and later according to another, yet neither description allows it to influence a distant event when the separation is space-like. For a causal connection to be possible, the second flash must lie within the future light cone of the first. The cone is not a physical shell expanding through space. It is a map of possibility, dividing events that can exchange influence from events that cannot. This is the meaning of causality that matters here. It is not the everyday demand that everything must have a reason. It is not the philosophical search for a first cause, and it does not automatically tell us why an event occurred. It describes a more disciplined relation, which events could, in principle, affect which other events, without violating the structure of relativity. Now perform a strange act of erasure. Remove every coordinate from the universe. Take away the rulers, clocks, grids, and labels. Forget the measured distance between every pair of events. Erase the angles and the familiar picture of a smooth arena. Leave behind only a vast record of relations. This event could influence that one. These two could not communicate. This event belongs to the causal past of another. What remains does not look like space. It resembles an immense network without a visible background. A pattern of ordered events whose connections say nothing obvious about meters, directions, or shapes. Yet that network may contain far more geometry than intuition suggests. If the pattern is complete, could it reveal where light cones must have been? Could it recover neighborhoods, dimensional structure, or the difference between a curved world and a flat one? Could distance itself be reconstructed from relationships that never mention distance? That possibility turns the title inside out. We normally imagine causes unfolding inside space, as though space were a theater built before the performance began. Objects occupy locations, signals cross the gap between them, and causes produce effects along available routes. From that perspective, space appears logically prior. It provides the separation, direction, and pathways that causal influence must obey. Relativity, however, does not preserve such a clean division. The structure that determines possible influence is inseparable from space-time geometry. Change the geometry, and light cones change with it. Paths once open to signals can close. Regions can become causally isolated. A black hole is dramatic, partly because its horizon is not a material wall. It is a boundary in the network of possible futures. This raises a reversal that classical intuition rarely considers. If geometry announces itself through the entire pattern of allowed influence, perhaps that pattern can define the geometry. Perhaps space is not the container in which causal relations happen. Perhaps what we call space is a stable, large-scale description of a deeper order among events. But three levels of claim must remain separate. Relativity's causal structure belongs to an extraordinarily successful physical framework. Mathematical theorems can establish what information a complete causal pattern contains under specified conditions. A theory in which causal order exists fundamentally before smooth spacetime is a further proposal, motivated by quantum gravity, but not confirmed by experiment. Moving from the first level to the third requires more than an evocative idea. It requires a reconstruction, a dynamics, and evidence that the reconstructed world resembles ours. So the investigation begins with a precise challenge. Start with a universe stripped of distance and geometry. Keep only the ordering of possible influence. Then ask whether the erased world can be rebuilt. The challenge also prevents a hidden mistake. We cannot ask what existed before spacetime as though a clock were already ticking outside it. Nor can we imagine causal elements floating inside an invisible room, because that quietly restores the space we removed. Fundamental priority is not necessarily temporal priority. It asks which ingredients a theory must assume, and which structures it can derive. If it can, causality and space may not stand in the simple order suggested by the title. If it cannot, geometry retains something irreducible that relations alone cannot supply. Either result forces us to examine what spacetime is made of, what physicists mean when they call something fundamental, and whether the arena of reality might emerge from rules that do not themselves live anywhere. For centuries, space seemed like the simplest part of reality. Objects could move through it, collide within it, or remain at rest against it. But the arena itself did nothing. In Newtonian physics, space provided an absolute framework of positions, while time advanced uniformly everywhere. Two observers might disagree about the speed of a carriage or a planet, yet they were assumed to share the same distances, the same durations, and the same universal present. That picture was powerful because it separated the stage from the performance. Matter produced forces. Forces changed motion. Space merely supplied the coordinates needed to describe what happened. Causality appeared to operate inside this fixed container. An influence left one location, crossed a measurable gap, and reached another location later. If the container already existed before any interaction was described, then space seemed naturally more fundamental than the causal processes taking place within it. Light made that separation impossible to maintain. By the 19th century, electromagnetic theory described light as a wave traveling at a definite speed. Yet attempts to fit that speed into ordinary Newtonian rules created a profound conflict. If velocities simply added, different observers should measure different speeds for the same beam, just as passengers measure a train differently depending on their own motion. Experiments did not reveal the expected motion through a stationary light-carrying medium. The deeper solution was not to modify light so that it behaved more like familiar objects. It was to modify space and time. In special relativity, every inertial observer measures the same vacuum speed of light. Preserving that fact requires observers in relative motion to divide space and time differently. They can disagree about lengths, durations, and whether distant events happen simultaneously. But beneath those disagreements lies a structure on which they agree: the space-time interval and the causal classification of events. Consider a flash and every event that could receive a signal from it. Those reachable events form its future light cone. Events that could have sent a signal to the flash form its past light cone. Between them lies the space-like region, containing events too distant to exchange any influence without something traveling faster than light. Different observers may assign different coordinates to all these events, but they do not transform a time-like connection into a space-like one. They preserve the cone. This was the crucial shift. Space and time were no longer independent containers. Hermann Minkowski expressed the new theory as a four-dimensional spacetime in which the geometry itself distinguishes possible causal relationships. The apparent movement of a light signal across space was only one observer's division of a more invariant structure. What could influence what was written into spacetime geometry? At this stage, spacetime still behaved like a fixed arena. Special relativity changed its geometry, but matter did not reshape that geometry. General relativity removed even this remaining separation. Einstein's gravitational theory replaced gravity as an ordinary force acting across a background with a dynamical metric. Matter and energy affect space-time geometry, and that geometry governs the paths followed by freely falling bodies and light. A clock deeper in a gravitational field can accumulate less time than a clock farther away. Light can follow curved routes around massive objects. Planets can move along trajectories that reflect curved spacetime, rather than an invisible pull transmitted across an untouched stage. These effects are not philosophical decorations. Gravitational time dilation must be accounted for in satellite navigation. Light bending has been observed from stars, galaxies, and massive clusters. The changing geometry around accelerating masses can propagate outward as gravitational waves, measured directly by interferometers. The arena has observable behavior. It can curve, evolve, carry disturbances, and determine how matter moves. Most important for our question, dynamic geometry also changes the structure of possible influence. Light cones can tilt and narrow relative to chosen coordinates. The future paths available from one event need not resemble those available from another. Near a black hole, this change becomes extreme. The event horizon is not a solid surface waiting to be struck. A freely falling observer may cross it without encountering a material barrier. What defines the horizon is causal structure. Once an event lies inside, no future directed light signal from that event can reach the distant exterior. The horizon, therefore, reveals something fundamental about Einstein's universe. Geometry is not merely a way to calculate distances after causal processes occur. It decides which causal routes exist at all. Alter the distribution of matter and energy, and the metric changes. Alter the metric, and the network of possible futures changes with it. This seems to offer a decisive answer. Space, or more accurately, space-time geometry, creates the conditions under which causes can produce distant effects. The cone comes from the metric. The metric determines which trajectories are time-like, which are light-like, and which separations forbid communication. Causality appears to be an output of geometry. But the conclusion arrives too quickly. Everything we know about the geometry is learned through physical behavior. Clocks accumulating different durations, objects following geodesics, and light tracing the boundaries of possible communication. Geometry tells matter how to move, yet the resulting pattern of motion tells us what the geometry is. A light cone may be calculated from the metric, but it can also be treated as evidence from which the metric structure is inferred. Imagine receiving no coordinate chart and no distance measurements, only a complete catalog of every possible light signal. For each event, the catalog identifies every event that could affect it, and every event it could affect. The information would reveal where causal boundaries lie. It would show which neighboring events share possible histories, and which are forever outside one another's reach. Would that catalog merely describe consequences of an independently existing geometry, or would it already contain the geometry in another form? Relativity has therefore changed the original question twice. First, it fused space and time into a causal spacetime. Then, general relativity made that spacetime dynamical. The old passive arena disappeared. In its place stood a geometry whose most important features were expressed through relationships among events. This is where the geometry first answer begins to weaken. If observers can discard their coordinate descriptions yet still agree about possible influence, causal order may be carrying the invariant core. The stage and the performance are no longer separated, even in principle. To discover whether those relationships are only products of geometry, we must now inspect them directly. We must ask exactly what survives inside the network of light cones, what information it preserves, and what remains missing when every ruler is taken away. Begin again with a single event. From it, imagine every path a physical signal could follow without exceeding the speed of light. Some paths lead into its future. Others, traced backward, arrive from its past. Together, they form the familiar light cone structure. Yet the cone is more than a boundary drawn around one flash. Repeat the construction for every event, and spacetime becomes a densely interlocking system of possible influence. This system is not merely a chronological list. Two events can be assigned times on a coordinate chart without being causally related. If they are separated by too much space and too little time, no light signal can travel between them. One observer may say the first event happened earlier. Another, moving differently, may say the second did. Neither ordering creates a physical contradiction because the events are space-like separated. There is no permitted signal whose cause and effect sequence has been reversed. For events that can communicate, the situation is different. If one lies inside the future light cone of another, all inertial observers agree on their causal order. They may disagree about the elapsed time or spatial distance, but not about which event can influence which. A causal relation therefore contains something more invariant than a coordinate timestamp. It identifies a structural connection that survives changes of perspective. Now expand this information across the universe. For every event, record its causal past and causal future. Two nearby events will have overlapping patterns. Events divided by a horizon may have an asymmetric relation. Signals can cross one way but never return. Curvature alters how cones fit together from region to region. Without measuring a single length, the complete network begins to reveal neighborhoods, boundaries, and the local organization of spacetime. The surprising richness of this network can be understood by considering what happens when geometry is rescaled. Imagine changing the metric from place to place in a way that stretches measured lengths and durations while preserving every light cone. Time-like directions remain time-like. Light-like directions remain light-like. Space-like directions remain space-like. The detailed readings of rulers and clocks change, but the pattern of who can signal whom does not. Such a transformation is called conformal. It preserves angles in the relevant geometric sense, and, most importantly here, preserves causal structure. If two spacetime descriptions differ only by a positive conformal factor, they agree on the routes available to light and slower influences. Their scales differ, but their cone structures match. This tells us both how powerful causal information is and where its limitation lies. The pattern of possible influence can determine the conformal shape of spacetime. It can reveal how cones open, tilt, overlap, and form boundaries, but it cannot, by itself, determine the local scale. A region may be assigned a different volume while retaining the same causal connections. Order distinguishes the architecture of the cones, not the final calibration of every ruler. A map offers an analogy. Imagine possessing every possible route between cities, but no scale bar. The routes reveal which locations connect, where barriers interrupt travel, and which places lie between others. Much of the map's structure can be reconstructed, yet the same connectivity could be drawn larger or smaller. The analogy is imperfect because space-time causal relations are richer than road connections, but its missing scale points toward the correct gap. There is another necessary caution. Reconstruction does not work without conditions. Physicists can write mathematical spacetimes containing severe causal pathologies, loops that return to their own past, or regions in which distinct events have indistinguishable causal histories. In such worlds, a catalog of pasts and futures may fail to identify events uniquely. The powerful reconstruction results apply to broad classes of well-behaved spacetimes, satisfying appropriate causal distinctions. One useful idea is that different events should have different causal pasts and futures. If two separate events possess exactly the same causal relationships to everything else, the network cannot tell them apart. The conditions known as past and future distinguishing prevent that ambiguity. They are technical assumptions, but their purpose is intuitive. The causal record must contain enough variation to label each event by its relationships. This is why the claim that causality determines geometry must be stated carefully. It does not mean that a handful of cause and effect arrows can reproduce the universe. It requires the complete relational structure, appropriate mathematical conditions, and an additional source of scale. Nor does it mean that causal relations produce geometry through a physical process. At this stage, it means that one description contains enough information to reconstruct much of another. The distinction between reconstruction and creation is essential. A portrait can be reconstructed from encoded data without the data having painted the original face. Likewise, if causal order allows a metric structure to be recovered, that fact establishes informational sufficiency, not necessarily ontological priority. Geometry may generate the causal pattern, the pattern may encode geometry, or both may be aspects of one classical structure. Even so, the result is unsettling for the simple geometry-first picture. If distances and durations were fundamental, while causal relations were merely consequences, we might expect erasing all measurements to destroy nearly everything geometric. Instead, the network retains the cone structure that organizes spacetime. It preserves the distinction between possible and impossible influence and reveals much of how local regions fit together. This insight did not appear suddenly. Long before modern quantum gravity programs, researchers explored whether geometry could be founded on causal relations. Alfred Robb attempted to build space-time concepts from relations of temporal order. Later work by E. H. Cronheimer and Roger Penrose developed abstract causal spaces. These efforts asked whether light and order were not just phenomena within spacetime, but tools for defining its structure. The historical program eventually produced rigorous reconstruction results. Their importance lies not in declaring causality the winner, but in exposing a near equivalence hidden inside relativity. The metric determines light cones. The full arrangement of light cones, under suitable conditions, determines the metric up to a conformal factor. Each side appears capable of recovering the other, except for scale. That missing factor now becomes the documentary's precision gap. A conformal geometry can tell us which events may influence each other, but it cannot fully tell us how much spacetime lies between them. It lacks the volume information needed to turn causal shape into complete Lorentzian geometry. If all rulers have been erased, where could that volume come from? One answer would be to restore a separate measuring field. A more radical answer is to ask whether spacetime contains countable ingredients. If volume were proportional to number, then counting events could supply what causal order leaves unknown. Before that idea can be taken seriously, however, the reconstruction claim itself must be made precise. The next step is not another metaphor, but a theorem showing exactly how much of a suitable spacetime is fixed when its pattern of chronological relations is known. The idea that causal relations might define geometry did not begin with quantum gravity. It developed through a longer attempt to identify which parts of spacetime were physically meaningful and which belonged only to a chosen coordinate description. Early in the 20th century, Alfred Robb tried to construct the geometry of relativity from a relation he called conical order. Instead of beginning with lengths and coordinates, he began with the temporal ordering revealed by light signals. Decades later, E.H. Cronheimer and Roger Penrose developed an abstract theory of causal spaces. Their work treated chronology and causality as mathematical structures in their own right, not merely as consequences calculated after a metric had already been supplied. The program reached a stage during the 1970s. Stephen Hawking, A.R. King, and P.J. McCarthy investigated how the paths of freely moving particles and light determine the topology of spacetime. Soon afterward, David Malamud proved a result whose meaning can be expressed plainly despite its mathematics. Take two suitably well-behaved spacetimes. Suppose there is a one-to-one correspondence between their events that preserves the complete chronological relation. Whenever one event can influence another along a time-like path in the first spacetime, the corresponding events have the same relationship in the second. Under appropriate distinguishing conditions, the two spacetime metrics must be related conformally. Their light cones have the same structure, even if their local scales differ. The importance of this result becomes clearer if we reverse the usual direction of explanation. Given a metric, physicists can calculate which curves are time-like, which are null, and which are space-like. That direction is familiar. Geometry produces the causal map. Malamud's result shows that the chronological map carries enough information to recover the conformal metric. Causal order is not a thin shadow cast by geometry. It preserves almost the geometric form. How can relations among events contain so much? Begin with topology, the structure that tells us which events count as near one another and which collections form continuous regions. In a well-behaved spacetime, combinations of causal futures and causal pasts define small diamond-shaped regions. Choose one event in the past and another in its future. The intersection of the first event's future with the second event's past identifies the events causally between them. Collections of such diamonds can be used to recover the spacetime's topology. Once this neighborhood structure is available, the causal relations constrain the smooth structure and identify the light cones at every event. The cones distinguish time-like, null, and space-like directions. Because the null directions define the conformal geometry. Preserving all chronological relations preserves that geometry as well. The network does not merely reveal that events are connected. Its overlapping pasts and futures show how the local causal neighborhoods must fit together. This is the first answer to the erased universe test. Remove the coordinate grid, distances, and clock readings, but retain every possible causal relation. For an appropriate spacetime, the surviving pattern can recover its topology, differentiable structure, and conformal geometry. The universe is not reduced to an unordered bag of points. Much of its arena remains encoded in who can influence whom. Yet one ingredient still refuses to return. A conformal transformation can multiply the metric by a positive factor that varies across spacetime, while leaving every light cone unchanged. The causal catalog cannot detect that rescaling, because all permitted and forbidden signal relationships remain the same. It knows the shape and orientation of the cones, but not the absolute calibration attached to them. This missing conformal factor carries volume information. Two regions can share the same causal ordering, while being assigned different spacetime volumes under conformally related metrics. Clocks can accumulate different proper times, and lengths can acquire different scales, without changing which events remain time-like, null, or space-like related. Causal order alone, therefore, does not recover the complete metric. The limitation prevents an exaggerated conclusion. Malament's theorem does not show that causality created spacetime. It does not describe a physical process in which geometry emerged, and it does not prove that causal order is the only fundamental ingredient. It establishes a rigorous reconstructive relationship inside continuum relativity. If the causal structure is known completely, and the necessary conditions hold, most of the geometry is fixed. Scale is not. The assumptions also matter. In pathological spacetimes, causal loops or failures of distinction can make separate events share the same causal profile. Then the relational record may not identify the underlying structure uniquely. The theorem concerns an important class of physically reasonable spacetimes, not every mathematical geometry imaginable. Its strength comes from precision, not universality without conditions. Even with those qualifications, the classical verdict is no longer one-directional. The metric determines the cones, but the cones determine the metric up to scale. Geometry tells light where it may travel, while the total pattern of possible light travel reveals geometry. Asking which one came first within classical general relativity may therefore be like demanding priority between two descriptions that nearly reconstruct each other. The word nearly is where the next theory begins. If causal order supplies conformal geometry, a separate principle must supply volume. In a smooth continuum, volume is assigned through the metric scale. But suppose the continuum is not fundamental. Suppose a finite spacetime region contains a finite number of elementary events. Then volume might be estimated by counting them. Double the number at a fixed fundamental density, and the corresponding spacetime volume doubles statistically. This proposal would combine two kinds of information. Order would determine causal shape. Number would determine volume. Together they could, in principle, recover the full Lorentzian geometry that causal relations alone leave incomplete. The idea resembles reconstructing a country from two records. The first lists every permitted route and reveals connectivity, boundaries, and relative organization. The second reports how many identical tiles occupy each region, supplying scale. Roots without tiles lack size. Tiles without roots lack arrangement. Together they approach a complete map. The analogy is limited, because fundamental events would not sit on a pre-existing country beneath them. Their relationships and number would be all the theory initially possessed. That final warning marks the conceptual leap. Counting ordinary events already located in spacetime would not make spacetime emerge. It would merely measure an arena assumed from the beginning. For causal order and number to be fundamental, the elements cannot be introduced as dots placed inside a hidden manifold. The manifold must appear only as a large-scale approximation, reconstructed from the discrete structure. This changes the scientific task. It is no longer enough to show that a known continuum can be encoded relationally. A fundamental theory must begin without smooth spacetime, define its elementary objects and laws, and then demonstrate why their collective behavior resembles a Lorentzian manifold. It must recover dimension, volume, locality, curvature, and eventually Einstein's dynamics, without quietly inserting them at the start. In 1987, Luca Bombelli, Juhan Lee, David Meyer, and Raphael Sorkin formulated a proposal built around precisely this reversal. At the smallest scales, they suggested, spacetime may be replaced by a locally finite causal order. Smooth geometry would not be the container of the elements. It would be the approximation produced when an enormous number of ordered events is viewed from far enough away. The reconstruction theorem had shown why the proposal was not arbitrary. Causal order already held the conformal structure. Discreteness offered the missing number. But turning those insights into a physical universe required a new foundation, one with no rulers, coordinates, or continuum hidden underneath it. The proposal, published in 1987, began with a reversal of the usual picture. Instead of assuming a smooth spacetime and placing physical events within it, Luca Bombelli, Juhan Lee, David Meyer, and Raphael Sorkin asked whether spacetime itself might be only an approximation. Beneath it, they suggested, reality could consist of elementary events connected by causal order. The motivation came from an unresolved collision between two successful theories. General relativity describes gravity as smooth geometry. Quantum theory describes physical systems through uncertainty, superposition, and quantized interactions. At extremely small scales, treating geometry as an infinitely divisible continuum may no longer be adequate. The Planck length, roughly 10 to the minus 35 meters, marks a scale formed from the constants of gravity, quantum mechanics, and relativity. It signals where familiar descriptions are expected to require replacement, but it does not prove that spacetime is made of discrete atoms. Causal set theory turns that possibility into a precise starting point. Its fundamental structure is a set of elements equipped with an order relation. An element is interpreted as an elementary spacetime event. The relation between two elements represents proto-causality. One lies to the causal past of the other within this proposed foundation. Calling this structure an order imposes discipline. If event A precedes B and B precedes C, then A precedes C. This is transitivity. The relation cannot form an ordinary causal cycle, in which A precedes B, while B also precedes A, as a distinct event. Depending on the mathematical convention, this is expressed through irreflexivity, or an equivalent anti-symmetry condition. The labels assigned to the elements carry no physical meaning. Calling one element number 17 and another number 42 must not create a new universe. Those rules alone define a partial order, but a causal set needs another condition: local finiteness. Between any two causally related elements, only finitely many other elements may lie in the intervening causal interval. This inserts discreteness without arranging the events on a regular spatial grid. A bounded spacetime region is represented by a finite count rather than an uncountable infinity of continuum points. The two ingredients perform different jobs. Order carries causal shape. Number carries volume. If a causal set approximates a continuum at a fixed fundamental density, the number of elements associated with a region fluctuates around a value proportional to that region's spacetime volume. A larger region contains more elements on average. Counting, therefore, supplies the scale that causal reconstruction theorems leave undetermined. This is the meaning behind the causal set slogan, often summarized as order plus number gives Lorentzian geometry. It is not a promise that every partial order secretly contains a smooth universe. It states the information strategy of the program. In a suitable manifold-like causal set, the relation records conformal structure, while cardinality records volume. Together they should encode the geometry needed at large scales. The proposal is radical because the elements are not supposed to sit inside a hidden background. Diagrams inevitably draw them as dots on a page, with lines rising through space. But the paper is only a representation. Fundamentally, there is no external distance between two elements, no surrounding room, and no continuous time flowing behind the order. Only the elements and their relations are initially given. This prevents a common misunderstanding. A causal set is not a crystal lattice filling an invisible container. A lattice already assumes spatial directions, regular distances, and a background in which the grid is placed. Its repeating pattern also picks preferred axes. Under a Lorentz boost, such a grid would reveal a special frame, conflicting with the symmetry that special relativity requires. Causal set theory must obtain discreteness without turning spacetime into that kind of rigid scaffold. The order relation is therefore Lorentzian from the beginning. It distinguishes causal precedents rather than nearest neighbors arranged along spatial rows. Smooth space appears only if the large relational structure can be interpreted as approximating a Lorentzian manifold. To make that statement meaningful, researchers use the idea of a faithful embedding. Imagine mapping the elements of a causal set into a candidate continuum spacetime. The map should preserve causal order. If one element precedes another, their images should have the corresponding causal relationship. The number of mapped elements in a region should also agree statistically with its spacetime volume at the chosen density. Finally, the continuum should not possess important geometric structure far below the discreteness scale that the causal set could never represent. A faithful embedding does not mean the continuum existed first in nature. It is a comparison test. Researchers begin with a known spacetime, generate or examine an order, and ask whether the discrete relations reproduce the continuum's causal and volume information. If they do, the causal set is called manifold-like with respect to that geometry. This distinction separates three claims that are easily blurred. First, a smooth spacetime can be sampled to produce a causal set reflecting its structure. Second, researchers may reconstruct properties of a candidate manifold from an appropriate causal set. Third, a fundamental law may generate such manifold-like causal sets naturally, without the continuum being supplied. The first two concern kinematics and reconstruction. The third concerns dynamics and emergence, and it remains far harder. The 1987 reversal therefore changes what a theory is asked to explain. Conventional continuum physics begins with locations and determines how matter travels between them. Causal set theory begins with ordered events and must explain why their collective organization can be described by locations, durations, volumes, curvature, and dimension. Space is no longer the vocabulary in which the fundamental law is written. It becomes part of what the law must recover. That ambition is supported by the earlier reconstruction results, but not completed by them. Malament's theorem begins with a continuum spacetime satisfying appropriate conditions and shows how its causal structure determines conformal geometry. Causal set theory removes the continuum from the foundation. It must demonstrate that discrete order and number can reproduce the smooth conditions under which those classical relationships become valid. The difference is like knowing that a digital image can encode a continuous-looking curve and proving that a particular physical process reliably generates the right image. The encoding principle may be sound, while the generative mechanism remains unknown. Causal sets possess the ingredients from which geometry could be read, but a universe requires more than ingredients. There are also immediate questions of uniqueness. Could the same causal set approximate two macroscopically different spacetimes? If so, the emergent geometry would be ambiguous. The expectation that a sufficiently rich causal set cannot faithfully embed into two very different continua is known as the causal set Hauptvermutung. It is a guiding conjecture with partial results, not a universally completed theorem. The theory must also recover Lorentz symmetry without a preferred lattice frame, extract dimensional and curvature information, and explain how local physics arises from a relation that is not spatially local in the ordinary sense. Each requirement tests whether the reversal is a real foundation or only a new encoding of geometry already assumed. The first test is especially revealing. If events are sprinkled into a continuum in a rigid pattern, Lorentz symmetry fails. If they are distributed randomly, the individual pattern looks irregular. Yet the statistical rule can avoid selecting a preferred inertial frame. This technique offers a way for discrete causal dust to resemble a smooth relativistic world. It also introduces a new tension. Randomness may protect Lorentz symmetry, but a sprinkling performed into a known manifold still begins with the geometry the theory ultimately hopes to derive. To move beyond demonstration, researchers must erase the manifold after sprinkling and ask how much can be recovered from the order alone. The 1987 proposal has therefore supplied a candidate answer to the missing scale: count the elements. It has also supplied a candidate answer to the title: causal order may be fundamental, while spacetime is emergent. But these remain the opening moves of a program. The next task is to see whether a discrete structure, with no hidden coordinates, can preserve Lorentz invariance and reconstruct the geometry it was designed to replace. A discrete spacetime faces an immediate problem. Place elementary events at regular intervals, and the pattern creates preferred directions. Rows, columns, and repeating gaps remain visible, no matter how tiny the grid becomes. An observer moving relative to that grid can, in principle, detect its special rest frame. The structure would therefore conflict with Lorentz symmetry, a foundation of physics. Causal set theory approaches the problem through randomness. Begin temporarily with a known Lorentzian spacetime, and distribute elements into it using a Poisson process at a fixed average density. This procedure is called sprinkling. The number of elements in any region fluctuates, but its average is proportional to the region's space-time volume. The causal order among the sprinkled elements is inherited from the light cone structure of the manifold. An individual sprinkling looks irregular. It does not display the symmetry of the continuum. The important symmetry belongs to the statistical law. Poisson's sprinkling does not introduce a preferred inertial frame, because the probability of obtaining a configuration depends on space-time volume, which Lorentz transformations preserve. Boosting the description does not expose hidden rows or irregular clockwork beneath the events. Randomness, therefore, allows discreteness without an observable lattice frame. But the claim needs care. No single finite pattern is unchanged point by point under every Lorentz transformation. Rather, the ensemble and sampling rule are Lorentz invariant. The symmetry is not visible as geometric neatness. It appears as the absence of a preferred frame in the distribution. Sprinkling provides a controlled laboratory for the reconstruction problem. Researchers know the continuum used to generate the causal set, then discard its coordinates and distances. What remains is the partial order and the number of elements. They can now ask whether discrete observables recover properties of the erased manifold. Proper time offers one example. In a continuum spacetime, a time-like path connects causally related events. In a causal set, the analogous object is a chain, a sequence of elements in which each precedes the next. For suitable sprinklings, the length of the longest chain between two elements is related statistically to the proper time between their continuum counterparts. No fundamental ruler is inserted. Duration emerges from the structure of ordered steps. Dimension can also leave a relational signature. Different dimensional spacetimes produce different probabilities that randomly selected elements will be causally related. Estimators developed in the causal set program use relation counts or interval structures to infer an effective dimension. The causal network can therefore reveal whether the manifold it approximates behaves more like 2, 3, or 4 dimensions, even though the fundamental elements carry no coordinate labels. Curvature is more difficult, but progress exists here as well. By counting specific kinds of causal intervals and combinations of relations, researchers have constructed discrete analogues of differential operators and curvature terms. The causal set, D'Alembertian, approximates a familiar wave operator under appropriate continuum conditions. The Benincasa-Dowker construction uses order-theoretic counts to approximate gravitational curvature and, in suitable limits, an action related to the Einstein-Hilbert action of general relativity. These achievements demonstrate that the order is not informationally empty. For causal sets known to arise from well-behaved manifolds, relational statistics can recover volume, time, dimension, and aspects of curvature. They make the phrase emergent geometry mathematically meaningful. Yet sprinkling begins with the answer. A continuum manifold is selected, and the elements are sampled from it. This proves that a suitable causal set can represent that manifold. It does not prove that an unknown causal set, generated by fundamental dynamics, can be recognized uniquely as our spacetime. The distinction between representation and emergence remains decisive. Suppose a causal set appears. Researchers must determine whether there exists a continuum into which it can be faithfully embedded. If one exists, they must determine its dimension and geometry. They must also ask whether a different continuum could fit the same order equally well. If multiple macroscopically distinct answers remain possible, emergent spacetime would not be uniquely defined. This concern motivates the causal set Hauptvermutung. In broad terms, it proposes that a causal set cannot faithfully approximate two continua that differ substantially at scales larger than the discreteness scale. The idea is essential because order and number should identify one large-scale geometry rather than several incompatible worlds. There are meaningful partial results and active mathematical work, but no completely general proof covering every relevant causal set and spacetime. The word manifold-like, therefore, carries a demanding burden. A causal set is not manifold-like merely because a diagram of it resembles scattered points. It must possess the relation patterns and number distributions expected from a sprinkling into a Lorentzian manifold. Most partial orders do not satisfy that standard. Even among promising candidates, reconstructing geometry is statistical and approximate rather than an exact conversion of every element into a continuum point. Lorentz-compatible discreteness creates another unexpected feature: non-locality. In a regular spatial lattice, each site can have a small fixed set of nearest neighbors. A Lorentzian causal set does not permit the same simple arrangement. Consider one element and the elements linked to it without an intervening element. Because surfaces of constant proper time extend through unbounded spatial directions in Minkowski spacetime, sprinkling can produce links reaching far away in a chosen frame while remaining causally immediate in the order. The result is a characteristic form of causal set non-locality. Fundamental adjacency is not equivalent to short spatial distance on one observer's time slice. An element can have many links that look spatially distant after a continuum frame has been chosen. This does not automatically permit controllable faster-than-light signaling. The links remain causal, but it means ordinary local field behavior must emerge through collective averaging and suitable operators, rather than being assumed through a fixed nearest neighbor grid. Non-locality is therefore both a cost and a signature of preserving Lorentz symmetry with discreteness. Removing the preferred frame prevents the theory from defining a universal spatial neighborhood at the fundamental level. What appears local in the continuum must be reconstructed from a deeper order whose connectivity does not match everyday spatial intuition. At this point, the causal first proposal has passed several important kinematic tests. A random sprinkling can avoid selecting a preferred inertial frame. Element counts track volume. Longest chains track proper time. Relation statistics can estimate dimension. Discrete operators and actions can approximate continuum expressions. These are substantive results, not declarations that space is an illusion. But they all begin with causal sets, chosen because they are already associated with suitable manifolds. Nature would not be allowed to consult a continuum blueprint before generating its fundamental events. A complete theory must explain why the causal sets produced by its laws belong to this rare manifold-like class. This separates three stages that should never be confused. The first is encoding. Take a continuum and represent it by a sprinkled order. The second is reconstruction. Erase the continuum and infer its properties from that order. The third is dynamics. Begin with no continuum and specify a law that makes the right orders physically dominant. Causal set theory has strong tools for the first stage and meaningful progress on the second. The third is where the deepest uncertainty begins. Even reconstruction contains unavoidable fluctuations. If volume is represented by element count, Poisson variation means two regions with equal continuum volume need not contain exactly the same number. Smooth geometry can emerge only as an approximation when many elements are considered. The continuums is not recovered element by element. It appears statistically as microscopic irregularities average into stable macroscopic quantities. This offers a clearer meaning of emergence. Smooth spacetime would relate to the causal set not as a magnified photograph relates to tiny pixels, but as a thermodynamic description relates to molecules. Temperature is real and measurable even though no single molecule possesses the temperature of a gas. Likewise, dimension, curvature, and distance could be real large-scale properties without belonging to any isolated causal element. The analogy explains collective behavior, but it does not guarantee that the necessary collective state occurs. The remaining question is therefore no longer whether causal dust can encode geometry. For specially prepared manifold-like sets, it can. The question is what selects those sets from the enormous space of all locally finite partial orders. To answer it, the theory needs dynamics, rules assigning probabilities or quantum amplitudes to possible causal histories. Those rules must respect the fact that element labels are meaningless, preserve causal consistency, and produce large structures resembling spacetime without placing them inside one. Only then can causal order claim to explain geometry rather than merely store it. The next step is to imagine a universe built event by event, with no external clock telling the events when to appear and no background space telling them where to go. If spacetime is not fundamental, its dynamics cannot be described as objects moving from one location to another. There are no locations yet. A deeper law must act directly on events and their causal relations, producing structures from which motion, distance, and geometry can later be inferred. One way to explore such a law is to imagine a causal set growing. Begin with a single element. Add another, placing it to the causal future of some existing elements, while preserving the requirements of a partial order. Continue one element at a time. The result is a sequence of increasingly large causal sets, each containing the complete causal past created before that stage. This description immediately creates a danger. The order in which a mathematician labels the elements during construction might be mistaken for physical time. If one element receives label 1 and another receives label 2, the labels appear to identify which was born first. But causal set theory cannot allow arbitrary bookkeeping to determine observable reality. Relabeling the completed structure must not change its physical content. The required principle is a discrete form of general covariance. In general relativity, coordinates are labels rather than physical furniture. In causal sets, element names and permitted birth labelings play a similar role. Two growth histories that differ only in arbitrary labeling but produce the same unlabeled causal set must represent the same physical outcome. The dynamics must assign probabilities in a way that respects this equivalence. David Rideout and Raphael Sorkin investigated classical sequential growth models under a set of such constraints. New elements are added without altering the causal relations already established among older elements. Transition probabilities obey label independence and a condition called Bell causality, which limits how unrelated parts of the existing causal set affect relative transition probabilities. Under their assumptions, the allowed stochastic dynamics can be characterized by families of coupling constants. The phrase Bell causality can be misleading if heard without context. It is not simply Bell's theorem transplanted unchanged into quantum gravity. Within these growth models, it expresses a locality-like condition on competing births. Spectators outside the relevant precursor set should not distort the relative probabilities of alternatives. Its role is to constrain the stochastic law while respecting causal structure. Classical sequential growth is important because it demonstrates that background-free causal growth can be formulated consistently. The law does not tell an element where to appear in space. It determines how a new event relates causally to those already present. Large structure develops through relations alone. Yet these models do not provide the final dynamics of quantum spacetime. They are classical stochastic processes, assigning ordinary probabilities to alternative growth outcomes. Quantum theory generally requires amplitudes, interference, and a broader measure over histories. A successful causal set quantum gravity must move beyond a universe that selects one branch through classical chance. There is also an interpretive puzzle. Sequential growth sounds as though reality objectively becomes larger when each event is born. That image appeals to those who want physics to contain a genuine passage of time. But the birth labels are gauge information, and different permitted labelings can describe the same causal set. Whether the formal growth represents an observable becoming or only a method of constructing histories remains debated. The mathematics should not be converted into a philosophical verdict without further argument. The deeper quantum program shifts attention from one growing order to the space of possible causal sets. Instead of assigning only classical probabilities, researchers seek a quantum measure, or path sum. Each possible causal history contributes an amplitude. Those contributions can reinforce or cancel one another, much as alternative paths do in other quantum theories. This difference matters because probability only adds positive chances. Quantum amplitudes possess phases. A family containing numbers of histories can therefore contribute nothing if its phases cancel, while a coherent family can survive. Abundance alone does not determine the result. This is difficult because the histories are not fields evolving on a common spacetime. The histories are candidate spacetimes at the fundamental level. They may contain different numbers of relations, different large-scale structures, and no shared background coordinates. The theory must compare them without smuggling in the geometry it is meant to explain. A path sum also requires weights. In ordinary quantum mechanics, a path's phase is related to its action. For causal sets, researchers need a discrete gravitational action constructed entirely from order-theoretic information. Counts of particular intervals and relations can approximate curvature for manifold-like causal sets. These constructions allow an amplitude to depend on a causal set's intrinsic structure rather than on coordinates assigned from outside. The ambition is not merely to generate many orders. It is to make the correct large-scale behavior dominate. A law could satisfy every formal symmetry and still produce universes nothing like ours. It must favor histories that admit an effective continuum, exhibit appropriate dimensionality, and reproduce general relativity where that theory is known to work. Classical sequential growth offers one laboratory for understanding covariance and causal consistency. Quantum path sum approaches offer another route toward interference and geometric dynamics. They should not be treated as interchangeable stages of one finished model. Both illuminate what a fundamental law must accomplish, while the full synthesis remains open. Related process first proposals push the reversal in other directions. Energetic causal set models, associated with Marina Cortez and Lee Smolin, treat events, causal relations, and transfers of energy momentum as primary. Spacetime geometry is expected to arise statistically from this network of processes. Such models reinforce the idea that relations might precede location, but they remain active theoretical proposals rather than experimentally established alternatives. Across these approaches, a shared lesson emerges. If space is emergent, dynamics cannot begin by asking how far apart fundamental events are. Distance belongs to the answer, not the input. The primitive law must refer to relational structures, transition rules, amplitudes, or conserved quantities that make sense before a continuum geometry has appeared. This requirement makes the notion of locality especially delicate. In familiar field theory, local interactions occur at neighboring points in spacetime. A causal set has no fundamental spatial neighborhood and may contain the non-local links required by Lorentz-compatible discreteness. The dynamics must eventually reproduce effective locality, without defining its basic transitions through a hidden spatial grid. Sequential growth provides an intuitive picture, but even a perfect rule for adding elements would not by itself solve emergence. Researchers must examine the distribution of completed causal sets produced by the law. Do manifold-like structures occur commonly? Are they stable at large scales? Does the effective geometry have 4 dimensions? Does it support matter and gravitational behavior resembling our universe? These questions turn dynamics into a problem of selection. The axioms permit an enormous range of locally finite partial orders. Some can approximate simple Lorentzian manifolds. Others branch, layer, or connect in patterns with no continuum interpretation. A fundamental law must assign their probabilities or amplitudes so unevenly that the physically relevant histories are not drowned by the rest. The scale of this challenge is easy to underestimate. Constructing one manifold-like causal set proves possibility. A theory, however, must contend with every allowed alternative. As the number of elements increases, the number of distinct partial orders grows explosively. Even a tiny individual weight for each unsuitable order may not be enough if unsuitable orders outnumber manifold-like ones by an overwhelming factor. This is the same tension that appears throughout statistical and quantum physics. Energy or action competes with entropy. A configuration may be disfavored by its individual weight, yet dominate because there are so many configurations of its kind. In causal set theory, entropy refers here to combinatorial abundance, not to the temperature of a gas. The question is, which families occupy most of the space of possible orders? Until that question is answered, a growth law can create causal structure without creating anything recognizable as space. It might generate elaborate orders forever, while never approaching a smooth manifold. Dynamics must do more than respect causality. It must explain why causality organizes itself geometrically. This reframes the title once again. The proposal that causality created space is incomplete unless the causal dynamics produces space naturally. Defining events and precedents is only the foundation. The decisive evidence must come from the behavior of the whole ensemble, where desired geometries compete with every structure allowed by the axioms. Researchers therefore face a counting problem before they face an experimental prediction. If one chooses a large partial order without carefully designed dynamical weighting, what does it typically look like? Intuition might suggest a tangled approximation to some irregular spacetime. The mathematics gives a far stranger answer. Most large partial orders do not resemble causal dust scattered through a manifold. They accumulate into highly organized, layered structures with no ordinary spatial interpretation. Their abundance is so extreme that they threaten to overwhelm the rare orders from which smooth geometry could emerge. The causal first program has reached its midpoint. It has shown how order can encode geometry, how number can supply volume, how sprinkling can respect Lorentz symmetry, and how relational laws might govern growth. Now the space of possibilities turns those achievements against the theory. The question is no longer whether a causal set can look like spacetime. It is whether almost every causal set looks like something else. There is a vast difference between finding one causal set that resembles spacetime and asking what a typical causal set looks like. The first task is constructive. Begin with a manifold, sprinkle elements into it, and obtain an order designed to preserve its causal structure. The second task removes that guidance. Consider all partial orders with a large fixed number of elements, and ask which kinds dominate simply because there are more ways to build them. Intuition offers little help. One might expect most orders to resemble chaotic webs, with relations scattered without recognizable organization. Instead, a powerful result from combinatorics shows that enormous finite orders are dominated by a surprisingly rigid family. In the 1970s, Daniel Kleitman and Bruce Rothschild studied how the number of partial orders grows as elements are added. Their asymptotic result revealed that almost all sufficiently large labeled partial orders have a layered form. In a simplified picture, the elements collect into three broad levels. Many elements occupy a large middle layer, while smaller groups sit below and above it. Relations run predominantly upward between these levels. The exact theorem contains qualifications and asymptotic details, but its physical message is stark. If one samples large partial orders without a dynamics crafted to change their importance, the overwhelming majority do not resemble events sprinkled into a low-dimensional Lorentzian manifold. They resemble highly connected layered structures. These orders are not disorganized. Their problem is that they possess the wrong organization. A manifold-like causal set contains interval patterns, chain lengths, relation densities, and local statistical features compatible with a continuum geometry. A dominant layered order packs its elements into a combinatorial architecture that lacks such an interpretation. Its connectivity does not approximate the causal neighborhoods of ordinary spacetime. The distinction can be pictured by comparing two ways of arranging a population. In one, individuals are spread through a landscape, with communication limited by a light cone structure. In the other, nearly everyone belongs to one of a few ranks, with dense relations between ranks. Both arrangements define order, but only the first can resemble events distributed through a manifold. The analogy describes organization, not literal people, or spatial layers at the fundamental level. Why do the layered orders dominate? Because there are extraordinarily many ways to choose the relations between large groups of elements while maintaining the partial order rules. Their combinatorial freedom produces an immense multiplicity. A manifold-like order may be possible, but possibility does not make it typical. This is the causal set entropy problem. Entropy here does not mean that the causal set is hot, nor does it refer directly to the thermodynamic entropy of matter. It means abundance in configuration space. A family has high combinatorial entropy when a vast number of distinct orders share its broad structural type. Suppose every causal set contributed to a theory with roughly comparable importance. Even if one unsuitable set were individually no more significant than one manifold-like set, the total contribution from unsuitable structures could dominate because there are overwhelmingly more of them. The desired geometries would become a negligible minority in the complete ensemble. The problem reaches deeper than aesthetics. Causal set theory does not merely need some histories that can encode smooth spacetime. It needs its physical dynamics to make those histories relevant at large scales. If the laws produce structures drawn from the combinatorially typical population, there may be no extended space, no familiar dimension, no approximate locality, and no regime resembling general relativity. This reverses the confidence built by sprinkling. Poisson sprinkling demonstrated that discreteness and Lorentz symmetry can coexist for sets derived from suitable manifolds. Reconstruction estimators showed that those sets can retain dimension, time, volume, and curvature, but neither result addresses how rare such structures are among all possible causal sets. A successful encoding may occupy a minute corner of the theory's configuration space. The midpoint revelation is therefore not that causal order lacks geometric information. It can carry remarkable geometric information. The revelation is that almost every allowed order carries the wrong kind of information. The central problem changes from reconstruction to selection. At first, the numbers appear fatal. If bad orders outnumber promising ones by an enormous combinatorial factor, how could any reasonable law overcome that advantage? Assigning a small penalty to each bad order may not be enough. Their individual contributions can be suppressed while their collective contribution remains dominant. Physics has encountered related situations before. In a quantum path integral for a particle, most contributing paths are not smooth classical trajectories. Typical paths can be highly irregular. Yet the observed large-scale motion can approximate a classical path because quantum amplitudes interfere. Histories near the appropriate stationary behavior reinforce one another, while many alternatives cancel through rapidly varying phases. The comparison is useful, but not a solution. It shows that individually strange histories need not prevent an ordinary macroscopic limit. It does not prove that causal set histories cancel in the required way. For that, researchers must identify an appropriate gravitational action, calculate its phase across the dominant families, and show that their enormous entropy is defeated by destructive interference. This distinction prevents two opposite errors. The first is to declare causal set theory impossible, because most kinematically allowed orders are non-manifold-like. Quantum theories are not uniform lotteries over histories. The second is to assume that interference will automatically rescue the theory because it works elsewhere. Cancellation is a dynamical result that must be demonstrated for the actual causal set ensemble. The layered order crisis, therefore, creates a precise test. Take the families known to dominate the counting. Determine the discrete gravitational action for their members. Weight each order by the corresponding quantum phase. Then sum their collective contribution. If the phases align, their multiplicity overwhelms the path sum. If the phases oscillate rapidly enough, neighboring contributions can cancel, turning an entropic giant into a negligible result. This is where the same abundance can become either the theory's destruction or part of its rescue. A huge family with nearly identical phase adds coherently and dominates. A huge family whose phase varies across its members can erase itself through interference. Number alone no longer decides the outcome. The detailed dynamics does. The challenge is formidable because non-manifold-like does not identify one simple structure. The Kleitman-Rothschild family captures the leading asymptotic behavior of large orders, and broader layered families extend the threat. But other unsuitable causal sets may survive outside the classes that are easiest to characterize. Suppressing one family does not prove that every wrong geometry disappears, nor is suppression enough to prove that a good continuum remains. A filter can remove many unacceptable candidates without selecting the observed universe. After cancellation, researchers must still determine which causal sets dominate, whether they are manifold-like, and whether their continuum approximation has the correct dimension and gravitational behavior. The entropy problem thus separates a negative and a positive task. The negative task is to eliminate or suppress the overwhelmingly common structures that cannot resemble spacetime. The positive task is to show that the remaining quantum ensemble produces a stable continuum resembling general relativity. Progress on the first does not automatically complete the second. This makes the crisis scientifically valuable. It transforms a broad philosophical claim about emergent space into a calculational demand. If causality is fundamental, its dynamics must explain why causal relations organize into geometry, despite the combinatorial pressure towards something else. The theory must earn spacetime. That demand protects the program from circular reasoning. Researchers cannot restrict the sum to manifold-like orders because those resemble the answer, unless a principle justifies that restriction. The selection must arise from dynamics, not from knowledge of the destination. The title now carries a stricter meaning. It is no longer enough to say that geometry can be reconstructed from causal order and number. To claim that causality created space, one must show how a law over causal orders selects a geometric phase. The word created refers not to a sequence occurring before time, but to a successful derivation from more primitive ingredients. Everything established earlier remains necessary. Causal reconstruction explains why order can encode conformal geometry. Local finiteness makes number available as volume. Poisson sprinkling protects Lorentz symmetry statistically. Discrete operators offer ways to approximate curvature and action. Sequential dynamics demonstrates that background-free growth can be constrained. But the entropy result reveals that none of these achievements guarantees a universe. The governing question has therefore changed. We are no longer asking whether some causal sets can look like spacetime. We know they can. We are asking whether quantum dynamics can make spacetime-like behavior emerge from an ensemble dominated, by counting alone, by structures that look nothing like it. The next move is to examine the proposed mechanism directly. Quantum histories carry phases, rather than ordinary positive probabilities. A discrete gravitational action can make those phases vary. If the variation is strong enough across the layered orders, their vast collective contribution may cancel. The apparent catastrophe of almost everything then becomes a calculation. Can the wrong worlds interfere themselves away? Quantum theory changes the meaning of a possible history. In an ordinary lottery, Each alternative receives a positive probability, and the probabilities add. If one family contains vastly more outcomes than another, its total probability tends to dominate, unless each outcome is strongly penalized. A quantum path sum does not work that way. Histories contribute complex amplitudes carrying phases, and phases can cancel. Picture each contribution as an arrow. Arrows pointing in similar directions add to a large result. Arrows pointing around the circle can sum to almost nothing, even when there are enormously many of them. This is destructive interference. It allows a large family of alternatives to become collectively insignificant, without deleting any member by hand. In ordinary quantum mechanics, the phase assigned to a path is determined by its action. The action is a compact quantity encoding the system's dynamics across that history. When the action changes rapidly between neighboring paths, their phases rotate rapidly and tend to cancel. Near histories where the action varies more slowly, contributions can reinforce, helping classical behavior emerge from a much larger quantum sum. For causal sets, the principle must be rebuilt without continuous paths or a background metric. The candidate histories are discrete orders. Their action has to be calculated from relations and counts alone. It cannot rely on coordinates, distances, or curvature fields defined on a manifold that the theory has not yet produced. Earlier reconstruction work provides the necessary bridge. On manifold-like causal sets, patterns of order intervals contain information corresponding to continuum geometry. Researchers can count how many elements lie in intervals of different sizes and combine those counts into discrete operators. The Benincasa-Dowker construction uses such order-theoretic information to approximate scalar curvature and the Einstein-Hilbert action under appropriate continuum conditions. Later generalizations produced what is often called the Benincasa-Dowker-Glaser, or BDG, action across dimensions. Its detailed coefficients are technical, but its role in the documentary is clear. It supplies each causal set with a gravitational quantity derived from its internal order. That quantity can enter the exponential phase used in a causal set path sum. This creates a direct test of the entropy crisis. Choose causal sets with a fixed number of elements. Sum over the allowed orders, weighting each by a phase determined by the discrete action. Then isolate the layered families known to dominate the raw counting. The question is whether their total contribution grows with their immense multiplicity or collapses through oscillation. The mechanism depends on a competition between two rates. Combinatorial entropy measures how rapidly the number of layered orders grows. The action determines how rapidly their phases vary as relation patterns change. If the entropy wins, the wrong structures dominate. If the phase variation is sufficiently strong, destructive interference can beat the numerical advantage. This is subtler than assigning each bad order a tiny positive weight. With positive probabilities, a sufficiently large number of tiny contributions can still produce a large total. Oscillatory amplitudes permit positive and negative, or differently directed complex, contributions to neutralize one another. The family can be huge precisely while its sum remains small. The causal set calculation does not begin by labeling an order bad and imposing a punishment. The same gravitational action, intended to approximate general relativity on manifold-like sets, is evaluated on the non-manifold-like orders. Their suppression, if it occurs, follows from the variation of their intrinsic action. This matters because it reduces the danger of circularly selecting the desired answer. To understand the strategy, consider the simplest threatening structures first. Two-layer orders place elements into a lower and upper layer, with selected relations running upward. Three-layer Kleitman-Rothschild-type orders add the dominant middle population and a richer set of relations. More general K-layer orders extend the family. Researchers analyze their combinatorics and action, then estimate their collective contribution to the partition function or path sum. The phrase partition function is borrowed from statistical and quantum physics. Here it represents a weighted sum over causal sets. Depending on the formulation and analytic technique, researchers may study Lorentzian oscillatory sums, analytically continued versions, restricted ensembles, or parameter regimes where calculations are controllable. These distinctions matter because success in one setting must not be inflated into a complete definition of quantum gravity. Boundary terms and choices of coupling also matter. A discrete action that behaves appropriately on one class or in one limit may require careful treatment when boundaries, finite size, or different dimensions enter. Suppression is therefore not one universal switch marked on or off. It is a result established for specified actions, families, and ranges of parameters. Even so, the program asks exactly the right scientific question. The entropy problem identified a calculable obstruction. The action supplies a calculable response. Instead of arguing philosophically that nature should prefer smoothness, researchers can examine whether quantum phases actually reduce the contribution of the structures favored by counting. The free particle analogy now becomes more precise. A quantum particle's path integral includes wildly irregular trajectories, but the action organizes their amplitudes. Causal set theory, likewise, need not require every fundamental history to resemble a manifold. It needs the aggregate quantum measure to possess a regime whose large-scale behavior is geometric. Non-manifold-like histories may be present while failing to control the observable limit, but the analogy also reveals the remaining burden. For an ordinary particle, the path integral is built on a background time and space, and the classical action is already known. In causal set quantum gravity, the sum is over the background itself. The theory must establish not only which histories interfere, but also that its discrete action, measure, and continuum limit reproduce gravitational physics. The calculations therefore proceed in stages. First, characterize the entropically dominant orders. Second, evaluate or approximate the action across those families. Third, combine the phase behavior with the number of configurations. Fourth, determine whether suppression persists as the number of elements becomes large. Fifth, ask what structures remain after the dominant bad families have been reduced. Each stage answers a different claim. Counting reveals the threat. Action evaluation reveals the possible mechanism. An asymptotic suppression result shows that the mechanism can overcome abundance for the studied family. None of these steps alone proves that manifold-like causal sets dominate the full theory. The distinction between exclusion and selection must remain visible. If a calculation shows that a broad layered family cancels, it has removed an enormous obstacle. But it has not necessarily selected four-dimensional spacetime. Other non-manifold-like families may survive. The remaining contribution may be difficult to classify. Manifold-like orders may avoid this form of suppression without becoming dominant enough to define a continuum phase. Nor does an analytic path sum result count as a laboratory detection of spacetime atoms. It is evidence about the internal viability of a candidate theory. It shows that a feared combinatorial obstruction may be dynamically controlled. Empirical confirmation would require predictions distinguishing the theory from general relativity and competing quantum gravity approaches. These limitations do not reduce the importance of the test. Before suppression results, the vast dominance of layered orders threatened the causal first program at its foundation, a theory whose generic structures could never resemble spacetime would fail before reaching phenomenology. Showing that dynamics can neutralize those structures is a necessary step toward an emergent continuum. The result would also unite ideas introduced separately. Malaman's theorem showed why order can retain conformal geometry. Local finiteness turned count into volume. Sprinkling demonstrated Lorentz-compatible manifold-like orders. Discrete curvature supplied a gravitational action. The entropy problem identified the competitors. Interference could now cause the competitors to cancel through the same dynamics intended to recover gravity. This convergence provides the documentary's strongest mechanism, but the evidence must land in the correct order. We first needed to understand why raw counting favors the wrong worlds. We then needed to see why amplitudes are not probabilities, and how an intrinsic action rotates their phases. Only now can modern suppression results be evaluated without mistaking them for magic. Beginning in 2018 and extending through work published in 2023 and 2024, researchers analyzed increasingly broad classes of entropically dominant causal sets. Their calculations produced the partial rescue the theory required. Across substantial regimes, the collective contribution of major layered families is strongly suppressed. The next question is exactly how broad that achievement is. Did the path sum merely remove one artificial example? Did it control the Kleitman-Rothschild orders that dominate the asymptotic counting? Did it extend to larger families of layered sets? And after those contributions cancel, do we know what is left? The answer will be encouraging, but it will not be final. Dynamics appears capable of defeating much of the entropy catastrophe. It has not yet completed in its entirety the positive task of deriving the spacetime we observe. The first major suppression results did not claim to derive spacetime. They addressed a narrower question that had threatened to prevent any derivation from succeeding. Could a causal set gravitational action neutralize the layered orders favored by combinatorial counting? In work published in 2018, Seth Loomis and Stephen Carlip examined non-manifold-like causal sets within a gravitational path sum. Their analysis showed that, over a substantial range of parameters, the rapid phase variation produced by the action could strongly suppress the collective contribution of important layered structures. Entropy did not automatically win. That result established the mechanism in a concrete setting, but the central asymptotic threat still demanded broader control. The Kleitman-Rothschild orders were not arbitrary examples chosen because they were easy to defeat. They represented the three-layer structures that dominate the counting of large, finite partial orders. A convincing rescue had to reach them, and the larger families surrounding them. Subsequent work by P. Carlip, Stephen Carlip, and Sumati Surya investigated the discrete gravitational action for these entropically dominant sets. They showed that the leading behavior of the Benincasa-Dowker-Glaser action on Kleitman-Rothschild orders could be related to a simpler link action. This connection allowed earlier suppression arguments to apply to the full gravitational action at the relevant leading order. The program then extended beyond the three-layer case. Work published in 2024 analyzed more general k-layer causal sets, where the number of layers remains small compared with the total number of elements. These broader families include the structures responsible for the dominant combinatorial threat. The analysis found that their entropic contribution could likewise be strongly suppressed by action-driven interference. Stephen Carlip's 2024 review summarized the significance carefully. The combined results show that almost all of the non-manifold-like causal sets captured by the dominant layered counting can be strongly suppressed across wide ranges of coupling parameters. The phrase "almost all" carries a specific scope. It refers to the entropically dominant classes controlled by the available counting and action arguments, not to a completed classification of every non-manifold-like causal set. That scope is still enough to transform the theory's prospects. Before these results, raw combinatorics suggested that manifold-like histories would be buried beneath an overwhelming population of layered orders. Avoiding them seemed to require an external restriction that would select spacetime-like sets by hand. The suppression calculations demonstrate that a gravitational dynamics can perform much of this negative selection internally. The wrong structures are not declared illegal. They remain among the histories included in the sum. Their amplitudes acquire phases that vary so strongly that the enormous family contributes little collectively. The action changes the effect of abundance. What looked like a fatal entropy advantage can become a source of cancellation. That feature matters for explanatory honesty. If researchers had limited the sum to manifold-like orders, it would assume the geometry it promised to explain. Dynamical suppression, instead, lets the relational law distinguish among histories, without consulting a continuum blueprint or inserting smoothness as a rule. This is the documentary's point of convergence. The reconstruction theorems showed that causal relations contain conformal geometry. Local finiteness supplied number as a measure of volume. Poisson sprinkling showed that a discrete order can approximate Lorentzian spacetime without a preferred lattice frame. Relation counts supplied estimators of time, dimension, and curvature. The discrete action converted those counts into quantum phases. The entropy theorem identified the dominant competitors. Suppression results then showed the phases defeating those competitors. Taken together, these ideas establish more than a philosophical possibility. They show a mathematically structured route by which causal order and number could underlie a geometric continuum. The route contains a proposed kinematics, reconstruction tools, candidate dynamics, a major obstruction, and a non-ad hoc response to that obstruction. This is the strongest responsible point at which to answer the title in favor of causality. A causal-first theory is not merely replacing the word space with the word relation. It can encode geometric information, preserve relativistic symmetry statistically, construct gravitational quantities, and use its own dynamics to suppress vast families that do not resemble spacetime. Smooth geometry could be a collective phase rather than a fundamental container. But the word "could" remains indispensable. Suppression solves a negative problem. It shows that major wrong answers need not dominate. Emergence requires a positive result. The histories left after suppression must form a regime approximating the space-time we observe. Researchers do not yet understand the remaining ensemble well enough to claim that this has occurred. Manifold-like causal sets are not eliminated by the same argument, which is encouraging. Yet avoiding suppression is not the same as dominating the sum. Other non-manifold-like structures may also survive. The space of causal sets is too rich for the controlled layered families to exhaust every possibility. What remains could contain promising geometries, unsuitable structures, or phases not yet classified. There is also a difference between recovering some continuum and recovering ours. A successful result must favor a large-scale spacetime, with the observed dimensionality and Lorentzian behavior. It must reproduce Einstein's gravitational dynamics in the appropriate limit, allow matter fields with realistic interactions, and explain why ordinary locality emerges despite fundamental causal set non-locality. The continuum limit must be controlled rather than inferred from isolated examples. Physicists need a regime in which increasing the number of elements produces stable macroscopic observables, with microscopic fluctuations averaging into predictable geometry. Dimension, curvature, and effective field behavior must converge in ways that can be calculated and compared with established physics. Nor do the suppression calculations constitute experimental evidence that spacetime is discrete. They are internal theoretical evidence. A serious objection to the program can be overcome by its candidate dynamics. This increases plausibility, but it does not distinguish causal set theory from other approaches to quantum gravity, or from a fundamentally continuous spacetime. The distinction matters, because theoretical consistency and empirical truth are different achievements. A model can survive a mathematical crisis without being nature's chosen description. To cross that gap, causal set approaches need observable consequences that are robust, distinctive, and not already excluded. Current proposals remain model-dependent and have not produced a decisive detection of causal discreteness. The partial rescue should therefore be neither minimized nor inflated. Calling it merely speculation would ignore years of concrete combinatorial and action-based results. Calling it the emergence of spacetime would claim the very step the researchers say remains incomplete. Its true importance lies between those extremes. For the title, the rescue changes the balance of possibility. Classical relativity had shown geometry and causality to be nearly mutually reconstructive. Causal set theory then chose causal order and number as the more primitive description. The entropy problem threatened to make that choice physically sterile. Suppression results show that dynamics can protect the causal first program from its most abundant competitors. The argument now has a coherent form. If fundamental histories are causal sets, their manifold-like members can encode Lorentzian geometry. If their quantum amplitudes are governed by a suitable discrete gravitational action, dominant layered, non-manifold-like families can cancel. If the surviving ensemble develops the right continuum phase, smooth spacetime can emerge. The first statement is supported by extensive kinematic work. The second has received significant analytic support for broad classes. The third remains the decisive open condition. Presenting all three as equally established would erase the boundary between achievement and aspiration. That boundary creates the climax complication. We now understand a plausible way for many wrong worlds to disappear from effective influence. We do not yet understand, with comparable control, why the right world must appear. The remaining task is no longer vague. Identify the unsuppressed causal sets. Demonstrate a continuum phase. Recover four-dimensional Einstein gravity and acceptable matter behavior. Control non-local effects. Establish uniqueness at macroscopic scales. Derive predictions capable of separating causal priority from alternative foundations. Until those steps are completed, the suppression program provides a partial rescue rather than a final verdict. It moves the causal first answer from elegant encoding toward viable dynamics. It does not yet move it from candidate theory to experimentally established origin. To decide what can honestly be said about whether causality created space, we must now examine everything the rescue does not prove. Removing wrong answers is not the same as constructing the right one. The suppression results show that major layered families need not overwhelm the causal set path sum. They do not yet show that the histories left behind organize themselves into the universe we observe. The first unresolved task is simply to identify those survivors. The known counting results describe the dominant layered orders with remarkable power, and the action calculations control broad families among them. But the space of all causal sets contains structures that are neither ordinary manifolds nor members of the best understood layered classes. Some may escape the established suppression mechanism. Until the residual ensemble is characterized, researchers cannot say what the path sum actually favors. The second task is to demonstrate a continuum phase. Finding individual manifold-like causal sets is insufficient. A quantum theory needs a collective regime in which large numbers of elements produce stable geometric observables. Dimension estimates should settle toward the observed value. Curvature and proper time estimators should behave consistently. Fluctuations should average into an effective smooth description across scales where general relativity succeeds. This continuum limit must also recover dynamics, not merely geometry. A structure may resemble a four-dimensional manifold while failing to satisfy Einstein's equations. The effective large-scale action must produce gravitational behavior matching tested predictions, with controlled corrections. Black holes, cosmological evolution, gravitational waves, and weak field gravity cannot be replaced by a vague statement that smoothness appears. Matter adds another layer. The observed universe contains quantum fields, particles, interactions, and gauge symmetries. A complete causal set theory must explain how matter propagates on or emerges with the causal structure, how it couples to discrete gravity, and why familiar quantum field theory becomes accurate at accessible energies. Recovering an empty geometric manifold would leave most physical phenomena unexplained. Locality remains especially delicate. Fundamental causal set links can connect elements that appear widely separated on a chosen continuum time slice. This non-locality arises from combining discreteness with Lorentz symmetry. It is not automatically a defect. But the theory must show why ordinary experiments are nevertheless described by effectively local interactions, and why no unacceptable signaling or large non-local corrections appear. The Hauptvermutung presents a related uniqueness problem. If one causal set could faithfully approximate two macroscopically different continua, emergent geometry would be ambiguous. The expectation that this does not happen for sufficiently well-behaved cases has partial support and continues to motivate active mathematical work. It is not a completed theorem for every relevant structure. Together, these demands form a positive emergence ladder. Characterize the survivors. Establish a continuum phase. Recover four-dimensional Lorentzian geometry. Derive Einstein dynamics. Incorporate realistic matter. Explain effective locality. Demonstrate macroscopic uniqueness. Each rung is necessary before the phrase causality created space can be treated as a physical result rather than a research program. There is then an empirical rung. A theory can be mathematically coherent and recover known physics while remaining one of several possible foundations. To determine whether nature uses causal sets, researchers need predictions that are distinctive, robust under model choices, and measurable. Current phenomenological ideas have not produced a decisive observation uniquely identifying fundamental causal order. This is difficult, partly because the discreteness scale is expected to be extraordinarily small. Directly resolving individual spacetime elements may be impossible with foreseeable instruments. Researchers instead search for accumulated or indirect effects, modifications to propagation, fluctuations, cosmological signatures, or consequences of non-local operators. Such proposals are constrained by existing observations and often depend on details not fixed by causal set kinematics alone. The absence of a decisive test does not make the program unscientific. Quantum gravity research frequently advances through mathematical consistency, recovery of established limits, internal predictions, and the gradual development of phenomenology. But the evidential category must remain clear. A promising analytic suppression result is not an observation of spacetime discreteness. Competing approaches also prevent an easy ontological verdict. Loop quantum gravity and spin foam programs begin from quantum geometric structures different from causal sets. Holographic and entanglement-based programs investigate whether geometry emerges from quantum information and correlation. Other discrete or algebraic approaches choose still different primitive ingredients. The comparison should not become a catalog. Its purpose is to expose underdetermination. Different microscopic frameworks may reproduce aspects of continuum spacetime. If several can recover known physics, mathematical emergence alone cannot identify which structure is fundamental. Distinctive predictions or deeper consistency results must separate them. Even the word fundamental may hide two questions. One asks which variables make the most economical microscopic theory. Another asks what reality is ultimately made of. Physics can provide powerful evidence for the first through explanatory and predictive success. The second may remain partly interpretive when two descriptions reconstruct one another. Classical relativity already illustrated this ambiguity. The metric determines causal cones, while causal structure determines conformal geometry under suitable conditions. That near equivalence does not tell us which description nature regards as ontologically prior. Causal set theory breaks the symmetry by postulating discrete order and number as fundamental. But the postulate earns physical priority only if its dynamics and predictions outperform the alternatives. The current status can therefore be stated without either dismissal or exaggeration. Causal set kinematics is well defined. Reconstruction techniques recover significant geometric information from manifold-like orders. Lorentz-compatible sprinkling is understood statistically. Discrete gravitational operators and actions exist. Major entropically dominant layered families can be strongly suppressed in studied path sums. What remains incomplete is the controlled positive derivation of our continuum. and a unique empirical signature. Those gaps are not minor details added after the central victory. They are the steps that would convert a viable causal first framework into an established account of spacetime's origin. The distinction between a sieve and a recipe captures the situation. Suppression provides a powerful sieve. Many structures that cannot resemble spacetime contribute little after interference. A recipe must also specify what remains, why it has 4 dimensions, how it obeys Einstein's equations, how matter behaves within it, and what observation confirms the ingredients. Causal set theory does not yet possess that complete recipe. This limitation does not erase the achievement. Before the suppression program, combinatorial entropy threatened to fill the theory with structures lacking any continuum interpretation. Demonstrating that candidate dynamics can overcome much of that threat is a genuine advance. It moves the question from whether causal order is immediately overwhelmed to whether the surviving sector contains the right geometric phase. The open frontier is consequently sharper than a generic confession of ignorance. Researchers are not merely waiting for a vague theory of everything. They can investigate the residual causal sets, phase structure, continuum observables, matter couplings, horizon reconstruction, and phenomenological consequences. Each result can close a specified gap in the emergence chain. For the documentary's title, this frontier fixes the strongest honest wording. Causality may be more fundamental than spacetime in a serious quantum gravity program. Classical theorems explain why that reversal contains enough information to be plausible. Modern dynamics has survived a major entropy objection. But no observation or completed continuum derivation shows that causality created space in nature. The alternative phrase, space created causality, is also too simple. In general relativity, space-time geometry determines causal structure, but causal structure nearly reconstructs the geometry. At the classical level, they are interlocked. At the proposed quantum level, their apparent symmetry can be broken in favor of causal order, but only by hypothesis and successful derivation. We are now ready to return to the erased universe from the opening. Its coordinates, distances, and smooth background were removed. Causal relations survived. We have learned that those relations can restore the cone structure, that number can propose a scale, and that dynamics can suppress many structures that fail to resemble geometry. One question remains before the final verdict. After rebuilding so much from order, exactly which part of the world has been established, and which part still depends on an unconfirmed theory? Return to the universe we erased at the beginning. Its coordinates are gone. No ruler reports a distance. No clock supplies a universal time. There is no visible grid on which events can be placed. Only the pattern of possible influence remains. Which event can precede another? Which pairs can exchange signals? And which are forever outside one another's reach? How much of the lost world can that pattern restore? Classical relativity provides the first answer. Space-time geometry determines the light cones. It decides which directions are time-like, which are light-like, and which separations are space-like. In that sense, geometry creates the conditions for causal influence. But the direction reverses. For suitable, well-behaved spacetimes, the complete causal pattern determines topology, differentiable structure, and conformal geometry. Add volume information, and nearly the full Lorentzian geometry can be recovered. Causality is therefore not merely a consequence with no power to reconstruct its source. At the classical level, neither side simply came first. Geometry determines causal structure, while causal structure plus scale reconstructs geometry. They are interlocked descriptions of spacetime, not stages in an ordinary sequence. Asking which existed earlier would already assume the time whose foundations are in question. Causal set theory gives a second, more radical answer. It proposes that the interlocking descriptions are not equally fundamental. Beneath smooth spacetime lie discrete events, their causal order, and their number. Order carries causal shape. Number supplies volume. The continuum becomes an approximate collective description, much as temperature emerges from microscopic behavior without belonging to one molecule. This proposal has earned serious support. Poisson's sprinkling shows how discreteness can coexist statistically with Lorentz symmetry. Relational estimators can recover proper time, dimension, and curvature from manifold-like sets. Discrete gravitational actions can be built from order alone. Most importantly, quantum interference can strongly suppress broad layered families that otherwise dominate the counting of possible causal sets. These results make a causal-first universe scientifically coherent. They show that the idea is more than a verbal claim that relations matter. Causal order can carry geometric information, and candidate dynamics can overcome a major obstacle to its emergence. They do not show that nature chose this foundation. The surviving quantum ensemble is not yet understood well enough. No controlled result has demonstrated that observed four-dimensional Einstein spacetime, realistic matter, and effective locality generically emerge. No decisive experiment has identified causal set discreteness or separated it from competing quantum gravity programs. Suppressing many wrong structures is not equivalent to deriving the right universe. The direct answer to the title must therefore have three layers. In tested classical physics, space did not simply create causality, and causality did not create space. Space-time geometry and causal structure nearly determine one another. In causal set theory, causal order and number are deliberately placed first. Smooth space and time may emerge from them, and modern results make that possibility stronger than it once appeared. In nature, the priority remains unconfirmed. We do not yet possess the positive continuum derivation or empirical evidence required to say that causality created space as an established fact. The erased universe can now be restored only in layers. Causal order gives back the architecture of the light cones. Counting gives a possible scale. Statistical reconstruction gives dimension, duration, and curvature for the right kinds of order. Dynamics can silence many structures that fail to resemble geometry. The final layer, the demonstrated emergence of our actual spacetime, remains missing. That missing layer is not an invitation to conclude that the question is unknowable. It is a defined scientific frontier. Researchers can study what survives the path sum, whether a continuum phase forms, how matter couples to causal order, and what observable consequences follow. Each result can move the title from possibility toward evidence. The deepest implication is already clear. The arena of reality may not be a container placed beneath everything else. Space could be a stable, large-scale summary of relationships that do not themselves occupy locations. Yet physics demands more than elegance before it replaces an arena with a network. For now, causality has not been proven to create space. Space has not been shown to stand independently before causality either. Classical theory binds them together. Quantum gravity may separate them, placing causal order underneath geometry. Whether the universe truly works that way will be decided not by which answer sounds more profound, but by whether the deeper rule can reconstruct the world we erased. Only then can a causal order become more than an elegant possibility and become a physical explanation.